Today, we're going to talk about another analysis of variance design. Analysis of variance, the never-ending topic. I can see by the excitement in many of your faces that you're saying, Dave, tell us more about another exciting way to analysis of variance. Well, I shall. I don't see that well, so maybe that's not, maybe it was discussed, I don't see it. But either way, I'm going to do this lecture. So, let's say you're interested in learning or forgetting, okay? Which is a pretty common thing. You can't use independent groups really. I guess you could, but would you want to have like a group that had 1 hour retention interval for remembering some list of words, a group that had a 24-hour retention interval, and a group that had a 1 day retention interval? I'm interested in forgetting over time. So I want to have the same people tested over and over again. I don't want to test 3 independent groups. It doesn't really make a, you could do it that way, but it's kind of, the point of forgetting is that one person or one jiggity or whatever forgets things over time. You get a forgetting curve. Same thing with learning. Like, I don't know how you would do a learning experiment that had independent groups. Time is the key variable. I mean, a definition of learning, I don't know, how do you guys take learning with Lori? Yeah, how does she define learning? Because I always define it as some event at time 1 affects behavior at time 2. Bob Scorl's definition, I think it's a pretty good one. In that definition, it says time 1 and time 2 of testing people. Right? So you can test the same people over and over again. In fact, you almost have to, right? Look at the change over time. So let's see what's happening at different times. Yes? So you get something that looks like this. There's your design now. It's 5 minutes, 1 hour, 24 hours, group 1, group 1, group 1. All the same group. Remember before we had group 1, group 2, group 3, or whatever. Here we get the same group being tested over and over again to get a forgetting curve. Yeah? By the way, that's not an honors thesis. People figured that out a long time ago. People forget stuff over time. Yeah, it's true. My all-time favorite honors thesis conclusion was by my old student, Bobby Russin, and Bobby's now a lawyer, but he was great. It was an interesting experiment he did, but it didn't really work. And the only thing he ended up finding was that hard tasks are harder than easy tasks. And it was great seeing him say that. So in conclusion, what I found is that hard things are much harder than easy things. If you have any questions, this is really nice. By the way, you know in your honors thesis, if you don't get an effect, it doesn't mean you fail or something. Like it's not your PhD or something, okay? It's the process, it's not the result so much. All right, so those of you scoring at home should have detected a problem. I've been rambling about, well, everything, but also especially independent events, observations being independent. The observations now are completely dependent. I tested Keegan 3 times. I can predict pretty well his score the 3rd time after seeing his score the 2nd time and the 1st time. Right? I test Richard 3 times. I think the Richard scores are dependent on each other, the Keegan scores are dependent on each other, the Madison scores are dependent on each other. Aren't they? Oh no. Events are supposed to be independent. Dave said you can't violate that assumption. And yes I did. I was not talking to myself in the 3rd person there. Dave doesn't do that. Thank you. Thank you very much. You know what? Why don't we just put that in the model? Hey, let's put the fact that we have the same people tested over and over again in the model. If we put that into the structural model, then the math behind it, and we can then figure out an effect of, we have different levels of people. We'll think of them as a variable. We'll think of people, we have a Richard level, and a Keegan level, and a Madison level. How much people are you? I'm Madison people, etc. So the model now looks like this. X equals mu plus tau plus pi plus epsilon. Pi in this case is not 3.1415927. Blah, 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 blah. It is not to do with circles. It's any score equals the grand mean plus the treatment effect. That all looks, this looks like the simple ANOVA we started with. And we got error. We've just thrown one thing in there. The effective subjects. I'm not going to call them participants. You cannot make me. I'm going to call them subjects. Because they might, maybe they're plots of land, I don't know. Or pigeons. Have I told you the story about an editor of a journal wanted me to change subjects to participants and they were pigeons in my account? And I said, I'm not doing that. I'm just not doing it. They didn't sign a consent form. They're participants. So I made it animals. I said, is animals okay? Can I call them animals? I was trying to do the right thing. That's what wrong with me. I just felt it was a new clause. Okay. Questions about that? We've just put in a new factor. That's all. We've put in this new independent variable. Weird to think of people and levels of people. It's pi for people. I think all the people should get pi. That's what I'm saying here. Horrible. It's odd thinking of people as a variable or subjects as a variable, and then the different levels being the different people. But really, that's what I'm saying. And that's what the math's going to do. So now your design looks like this. 5 minutes, 1 hour, 24 hours, subject 1, subject 2, subject 3, subject 4. And then we have, so we need a fourth. Who's going to be our fourth? It's going to be Diamond. She's our fourth person. And we also have gender balance. Okay, very good. 1, 2, 3, 4. 5 minutes, 1 hour, 24 hours. Nice. So we've decreased epsilon, but we've paid for it. What do you mean we've decreased epsilon? Well, think about this. We had our original model for not being able to find an eraser. You apply them all the time. So the original model for one-way analysis of variance is this: x equals mu plus tau plus epsilon. Our new model is x equals mu, well that stays the same, plus tau, well that's the same, plus pi plus epsilon. So these are all the same, right? So that means that before it would be contributing to error. If we analyze this as a one-way analysis of variance, the effect of individuals would be due to, would go into the error effect. But we've now split it out. We've split it out. Does that make sense so far? Questions about that? Because you got mu and tau are already there. There's only one place pi can come from, and that's from epsilon. Pi comes from epsilon. It sounds like the worst Star Trek episode ever. Mr. Spock, plot a course for epsilon 3 to get some pi. I've been watching the original series again. And God, isn't it ever misogynistic? It's horrible. It's so progressive for 1967, you know, but man. Wow. Like I'm a 52-year-old white man if I'm offensive. That's like, what?
They made a Black Mirror episode about that.
Yeah, that's right. It's good. That was a really good episode. Actually, that hasn't been a bad episode of Black Mirror. Okay. Now, here's the second part. We paid for this. It's nice to make errors smaller because errors could be in the bottom of our analysis of variance equation. Or, our F test, right? Because the bottom, the denominator, let's do a numerator, denominator. The denominator is the epsilon part, right? If we make that smaller, we make the fraction bigger. Yay, big fraction. Big fraction means easy to find significance, right? But when you split this off, it takes some degrees of freedom away from error. If you take some variance away, it has to go somewhere. It takes along its degrees of freedom. So now we have fewer degrees of freedom for our error term. Does that make sense? And that's a problem because, well, it might be. If you look at an F table, the fewer degrees of freedom you have, the bigger the critical value, right? The value you have to exceed is bigger. If it's bigger, it's harder to find significance. So we've made the number bigger, but we've paid a price. We paid 14 degrees of freedom. So you can see this is what happens. Retention interval, that's what the independent variable is. We have, this is the old one-way ANOVA. We can analyze that one-way ANOVA, I guess, and we get something that looked like this. Retention interval, error, there's our total. For the repeated measures, we get this. This, retention interval, subjects. Why is subjects 3? Well, we had 4 subjects. N minus 1, little n minus 1, so it's over 3. We have 11 total degrees of freedom. There's a finite number of degrees of freedom in any design and a finite number of amount of variance. So what's left is 6, right? 2 and 3 is 5. I have to add up to 11, so it's 6. Error now has only 6 degrees of freedom. And if you looked in a textbook and you found out what the critical value for F is for 2 and 9 degrees of freedom, it will be smaller than it is for 2 and 6 degrees of freedom. So it's harder to find significance, right? But we're dividing by a smaller number. So that's good. Was it worth it? Almost always yes. Almost always yes. This ends up giving you more statistical power to it. Okay. Questions so far? So any designs that say there's a finite amount of variation and a finite number of degrees of freedom, we've partitioned the degrees of freedom and the variance a little bit further. That's all we've done here. Mean squared retention interval, mean squared treatment if you want to call it that, will be the same for both of those things. Because look, notice how the degrees of freedom didn't change. So those mean squares are going to actually be exactly the same number. Just like I said when I was breaking down from the model here, we use the same, the tals are the same. So the question is the reduction in mean squared error worth the loss of degrees of freedom for error? And the answer is almost always yes. Okay? You could probably cook up an example where it was no. Yeah, I probably could. But it's almost always the case that it's worth it. Okay? Almost always worth it. And you will note that your next assignment, which is posted on my website, which is due in like a couple weeks, that's one of the questions. Was the reduction in error worth the price you paid in degrees of freedom? Okay. So think about this right now. Let's just think about this. Is this realistic? Mu plus tau plus pi plus epsilon. In other words, we're saying that the effect of retention interval is exactly the same for Keegan as it is for Madison, as it is for Richard, as it is for Duncan. Is that fair? Does that make sense? Like, does everybody forget things at exactly the same rate?
I think it's fair to make the assumption.
Does the world actually work that way?
No.
Exactly. So it's probably a bad assumption to make that. It's probably bad to make that assumption because when assumptions fall out of the model, like when they actually come from the model, that's saying you can't screw with it, you can't violate that, except we know we would violate that every freaking time, right? Except if it's some really basic. I can't think of anything. Maybe a physical process of some sort, but something that involves anything with biology. There's going to be variance in there, right? So some people have way better memories than other people. You might have different strategies for studying the list of words I've given you. We've got, let's see, 2 men, 2 women. We've got 3 people who wear glasses. It's funny how I picked the people. There's 5 people with glasses in the room, and I picked more than that. My God, almost everyone in this room can't see. That's great. That is me. So we got 1 person who doesn't wear glasses, but don't tell me you wear contacts or anything. I don't want to know, because it's going to screw my example up. Maybe the words were hard to read. Okay? And so you guys didn't do as well as she does, because it's a little easier for her, because she can read a little bit better, because she doesn't have to, her eyes work better. I don't know. I was trying to think of something that was obviously different. I don't know. So that's not really a safe assumption. You're right, it would be an assumption we could make, except that it's such a basic one because it's about the model, we don't want to make this assumption we're going to violate all the time. Pi should interact with tau, which is exactly what I'm describing. Different people forget things at different rates. The effect of forgetting depends upon the person. Hey, that sounds a lot like a two-way interaction. In fact, that's exactly what it is. So it makes more sense to assume that tau and pi interact. So our model, the out model, compared to the in model, this model is completely out. It's comfortable with sexuality. Our model changes. Out model. I've got to remember to change that. I won't, but I have to remember to. So now our model is x equals mu plus tau pi, which it sounds suddenly like we're naming off a fraternity. Are you in tau pi? It's so great we don't have them. They're the worst. I love tau pi, it's delicious. So, does that make sense? That's our new model? Okay. So that's our model, x equals mu plus tau pi. And you're thinking to yourself, there's no epsilon? How could there be no epsilon? There's no epsilon. There's nothing left. We've exhausted the degrees of freedom. There aren't any left. Because think about this. If we have, like our example, we had 11 degrees of freedom total. We have 2 for retention intervals, right? We have 3 for subjects. The interaction is 2 times 3 is 6. Let's see, 2 and 3 is 5 and 6 is 11. What do we have for error? Oh, nothing. We're done. You can't have 0 degrees of freedom. You can't calculate something. That would mean you were dividing by 0. You can't do that. You know that. You divide by 0 with your calculator, you get a little thing that says E, which means error, or undetermined, or it'll say something like that. Make sense? So that's what we can't. Next, we could, we can't. So we won't. We treat S subjects, I'm just going to call that variable S. We're going to treat it as any other variable, even though it's kind of my old stats prof always called it a pseudo variable or a pseudo factor. Because really, it's different people. But we're going to treat subjects, our 4 subjects here, as a variable. And they're going to have 4 levels. That variable has 4 levels. Right? And we're going to arbitrarily, instead of calling the levels Madison and Keegan and Richard and Diamond, we're going to call them 1, 2, 3, and 4. There's 4 levels of variable. So in fact, it turns out that it comes out exactly the same way. It's just, the point here is that, yeah, had we done it the other way, it would have been fine. In fact, if we calculated it, it would be exactly the same way if we called it error. This is more of a theoretical thing right now. It won't be in a moment. this work then? Our error term is actually a treatment by subject interaction, because you might be thinking, how do I divide by mean squared error? There's nothing there that's called error. I can't divide by anything. It's not, what do I do? I have to quit school. You probably were thinking that, I hope. None of you. Stay at school, kids. So treatment by subject interaction. Subjects are a random factor, so the expected value work out that, remember that stuff I taught just the other day, and I said fixed effects and mixed models, and you're like, oh, why is it telling us this? And he said it never happens. Well, this is the special case where it happens all the freaking time. Subjects are a random factor. Yes, I know I didn't randomly choose you for, but it's a lot closer to a random factor than a fixed factor. I don't only care about the four of, well, I care about all of you, but I don't only care about the results of just the four of you. I want to generalize it to the humans. So I'm going to treat subject as a random factor. And if you remember what happens with the expected values of these mean squares, do I have that on here? I don't think I do. We're going to end up with, let's see, treatment effect plus treatment effect by pi. So the expected value for treatment is that. The expected value for subjects is going to be this, pi. And the expected value for the treatment by subject interaction is going to be the treatment by subject interaction. Because it's a mixed model. And you look at that and say, well, how am I going to isolate the treatment effect when I'm going to divide by the treatment by subject interaction? How am I going to test the subject effect? You can't. There's nothing to divide by. There's nothing that has a denominator we can divide by. We got pi, we want to isolate just, you can't. It's impossible. It's impossible. When you fail English, that's impossible. So, usually when people hear about this, like, we just leave it there? Yes. We can't test mean squared for subjects. It's impossible. It cannot be done. There is no error term with the correct expected value for its mean squared. There just isn't one. Like, it can't be done. There is no error term. Also, who cares? What a revelatory statement it would be if we found out that different people were different from each other. Wow, you found a subject effect? You mean different people are different? Ooh, call nature and science. No, that would be a result we'd be interested in anyway. All we're using this for is so we can get rid of some variance. You're saying that Diamond is different than Richard is different than Keegan is different from Madison? That's impossible. They must be exactly the same. They're clones. No, they're not. They're different from each other. People are different. People are people, so why should it be Depeche Mode? Anybody? No? Okay. It's a lot. Like your parents would have got that joke. Paul and I were talking today about how our cultural references now, your parents would find them hilarious. But we don't. Neither of us care. But it would be nice if you could just pretend. That was nice. It's not an interesting thing anyway. Even if you could test it, why would you test it? Who would give a crap that we found out that people were different from each other? It's not an interesting effect. Do you see that? So it's cool. We don't have a way to test it, but we don't need to care. Good. Okay. Questions so far? So that's repeated measures. That's really just the basic idea behind how repeated measures designs work. Okay. You okay? You guys, everybody okay? I just sort of looked at you, but I'm looking at different people. Is everybody okay? Everybody okay? This makes some sense? Right, so now you see why I taught you that expected value mean square thing? You okay? Now, you might think to yourself, do I have to figure out what the expected values are of mean squares whenever I do a design? There was a time when we did. I'm going to show you a really neat trick. Maybe today, but probably on Tuesday. Okay. Remember matched pairs or correlated t-tests, as it's sometimes called? Right, where you just match people up and then you treat them like it's repeated measures. Well, we can do the same thing here with analysis of variance. So before and after, or instead you have the same subjects and you match them on a variable. So this is called a randomized block design. And we usually match the subjects on the dependent variable. Okay. So if we were doing testing 3 different blood pressure drugs, we would find 3 people with the same blood pressure and put them in what we call a block and treat them like with the same subject. That's the case, and when Keegan said it's sensible. Within a block, it's sensible, yes. It's that assumption that can be made. If we've already pre-measured and matched them on something. Okay. Just what we would do with a t-test, repeated measure t-test, right? So by extension then, we can do exactly the same thing with repeated ANOVA. We're basically going to use something that looks a lot like repeated measures analysis of variance, but we're using different people. So we take subjects and we block on, what we need is something called homogeneity of experimental units. That just means that within each block, as it's called, we have the same score for something we've blocked on. So again, if it was blood pressure, we'd find 3 people that have the same blood pressure. That's the homogeneity part of experimental units, all the same. Okay? And then we test them on some blood pressure. Then we find 3 other people and we test them on blood pressure. Now, you could do it matched pairs or matched triples. You could, litter mates is often used as a blocking variable, etc. It's exactly the same logic as the correlated or dependent sample t-test, except we're going to do it with analysis of variance system. So we're going to block on a variable. We call this variable, when we block on, we call it a nuisance variable. It's a variable that gets in the way, but we can measure it. Oh, it's measurable. That's nice. Okay? This is going to reduce epsilon, reduce error, any error we have, and give us more power. The model is very similar to the one we've seen before. So the repeated measures is actually a special case of blocking. Of a randomized block design. It's a special case where with a block, in fact, it's the same person. Here we're just going to use people that have been blocked on whatever the nuisance variable is. Before the nuisance variable is individual people, because people are a nuisance. So the structural model actually looks like this. Oh, it looks like the one we started out with. X equals nu plus tau plus pi plus epsilon. Any score equals the grand mean plus the treatment effect plus the effect of the block plus residual, it's called here. What's left over? So the residual is just what's left over. Some assumptions. The effect of treatment sums to 0. It always does. That the effect of blocks, they're normal and independent with a mean of 0 and a variance of sigma squared sub pi, and that the residual, the error, what's left over, is also normal and independent with a mean of 0 and a variance of sigma squared sub epsilon. They're the standard kind of assumptions we're going to make, okay? Nothing to worry about. Error is independent of pi, independent of the block here. That's an important assumption you can't violate. So I keep looking at my phone, I keep thinking my son's texting me. I keep vibrating because I get so many damn messages, so I'm sort of. I am paying attention. No, it's common courtesy that, you know, if you're supposed to be up here putting on a show and you guys pay for it, and you think I'm actually just going to look at Facebook for a while. No, I'm always concerned that my son's texting me because he does now. And it's always something like, there's no money left in my bank account or something like that. No, that wouldn't be the case today. I was allowed yesterday because I got paid yesterday. Not enough, but I got paid yesterday. Actually, it's not that bad. There's also no interaction of any sort. No tau by pi interactions. This is a really strange assumption because before I was saying with people, we can assume there's an interaction. We can actually measure that. The problem here is we can't measure the interaction between the effect of a block and the effect of treatments. So if we put people in different blocks, there's not any variant, we can't measure it, like there's no way we can calculate it, is what I'm saying. We can put it in there, there's a way you can do it, I'll talk about that at the end, but it's really annoying. It doubles the size of your design, no one wants to do that. So there's no interactions. But what if there is an interaction in the population? Like, just because we say there's no interaction doesn't mean there isn't one. So what if there is one? Well, error is going to increase because the only place unexplained variance can go is error. Right? It's the only place unexplained variance can go live. Is in the error term. So you'll lose power. The only upside of this is you're not going to make false positives. You're not going to say there's an effect when there isn't one, but there might be an effect and you miss it. Okay? So the best thing you can do here is actually not have interactions. The problem is, how do you know there's no interactions if you can't actually measure them? That's going to be hard, because if you knew the answer, you wouldn't do the experiment. That's always the thing, right? So you have to look at, this is where the power of exploratory data analysis. So here's an example. We have 3 methods of teaching. And let's say it's teaching French as a second language. My wife does that. So let's say it's teaching French as a second language. A couple of you have taught you. So the point here is that people who come in and, as much as it's actually impossible in Ontario not to take French in high school, people somehow don't learn anything. So we can pretend that they actually only got French to grade 8. What do you have to do? Is it to grade 10? Mm-hmm. Yeah? So you have some people, well, let's maybe grade 10. Some people that only have French up to grade 10. Some people who may have gone to French immersion, and some people who are actual francophones, actual living, breathing French speakers. They come from, I don't know, Hearst or Longueuil or something, or Brussels. There's an Altonic guy once from Chad. It's like this. They speak French there, or Cameroon, or one of the old French West African colonies. And she would tell you that one of the problems is that when you have these different groups of people, how do you teach them? Because you get one group of people that come in and take intro French, they don't even know their colors. Literally, like they're like, well, I know, I can count to 7. Un, deux, trois, quatre, cinq. It's really, the first time I walked by a classroom and I heard her teaching colors, I thought, really? But then, yeah. Okay, fine. And then you've got people that went to French immersion and can speak decent French, and you have people, actual francophones, that take these things and they shouldn't be taking those courses. It'd be like you going into an ESL class. If you don't nail that and get a freaky A+, You should nail that. That's what I'm saying. But you have different teaching methods. So maybe you've got sort of straight ahead lecture method. Maybe you've got, I don't know, what's another teaching method? Oh yeah, what do they call it? The flipped classroom, which is all the rage now in the education literature, which is where basically you do all the work and I just stand here. That's not exactly what it is, but it's a lot of interactive exercises. And the third method will be, I know, maybe the third method is the idea that it was floated here a few years ago of only taking one course at a time for, say, 4 hours a day for 3 weeks. And that's all you take. And then when you're done that class, you take another class for 3 weeks. Which is done at some very prestigious small liberal arts colleges in the States, and I really wanted us to do that. But some people don't like change, so we never do. I'm afraid of change. I'm going to have to work harder. So, think how cool that would be? Imagine that. You just take this for 3 weeks. I know that sounds hellish, but it would be done. You wouldn't have any other assignments in any other classes. Pretty cool, right? No, I don't like it. It's weird. Anyway, that's our 3 methods. And we know that different levels of past experience, let's say teaching French, and knowing French, is going to have a real effect on how well you respond to those different methods. So we can block on those methods. And we got 9 people in a French class. Okay. So we got low experience, medium experience, high experience. I don't know what we're measuring there. Because I just threw numbers into a spreadsheet and it printed out a graph. Doesn't really matter. You would look at that and say to yourself, can I use randomized blocking? Because it'd be great because I can reduce error. But there looks like there's interaction, right? Because the effect of method changes depending upon the block you're in. But it's not that intense interaction. It's not this ordinal. And my advice would typically be, if it's an ordinal interaction, who cares? You're probably going to find the effect you're interested in. Right. But if you have a disorderly interaction, you just can't use this method. You just say, well, sorry, don't treat it as randomized block. You're just going to have to have a bigger error term. That's just the way it's going to be. I don't know what to do with this t-shirt underneath here. It's too long, and then I end up looking like underneath the sweater I'm wearing a dress. I'm tucking it and tucking it. You might be thinking to yourself, does Dave ever think of things and not say them? Not very often. You can have more than one repeated measures variable. So the randomized block, or the repeated measures, is a special case of randomized block. You could have more than, 5 minutes per hour, 24 hour, implicit and explicit memory, and we're going to test the same people. All group 1. Wow. How the hell are we going to deal with that? Okay. So what's the model here? It's x equals u plus alpha plus beta plus alpha beta plus pi plus alpha pi plus beta pi plus alpha beta pi. That's our model. Because remember, we're just treating subjects as a variable. We're just treating people, pi, as a variable. The math doesn't know it's you individual people, so the math doesn't care about your individuality. The math just thinks of you as being just some other set of numbers. The numbers don't know where they came from. There's a lot of terms here, and probably many potential error terms. Remember, we used tau pi as an error term. Interaction of the effect we're interested in, and subjects. So it looks like there's a lot of potential error terms here. This one, and this one, right? Alpha pi, beta pi, and alpha beta pi. Just starting to sound like something from Dr. Seuss, right? It looks like this. So what we have, there's a way to do this, to figure this out, is you list subjects first, which is what I've done, and then take your first independent variable, retention interval, and then we go subjects by retention interval. And then we list the next, and I'm going to call M for memory, okay? For implicit versus explicit. And then we cross it with this, and this, and this. See? M by S, M by Ri, M by S by Ri. If you actually list out the terms in that order, the way I just did this, so list your subjects, then list your variable, then list the interactions of it with everything above it, and just keep doing that and adding in new ones, you will be able to find out what the error terms are. You're going to test retention interval with retention interval by subjects. The one below it has subjects in it. Memory with memory by subjects. Interaction with subjects by interaction. So it's totally doable to figure out what these error terms are without actually having to sit down and work out the expected values of the mean squares. It's a little trick. We're going to keep building on this little trick up until before I go to Florida at that conference. That's in April. So we're going to build on that little trick, and this is called it's called Yates order, and it's something that was developed by Frank Yates. You've heard the guy who developed, bunch of those post hoc tests, things like that. He's a very famous statistician, and this is the way he did things. This is an algorithm he came up with of figuring out what error terms are simply by listing subjects, then within subjects effects or repeated measures effects, and then interaction. See what happened here? Subjects, retention interval, subject by retention interval. Memory by subjects, memory by retention interval, memory by subjects by retention interval. Go to the one below it that has the thing you're interested in, and subjects. That's your error term. Now you don't have to sit down and work out the expected values of mean squares. I mean, if you want to, you can. Why would you do that? It only works, by the way, when your independent variables are fixed factors and all of your figure subjects is a random factor, but that's almost always what we do. Questions about this stuff? All right. So let's back in, and I'll see you guys on Tuesday.